There's no doubt that servicing today's automotive electrical systems can be complicated. Some models may have as many as 50 individual wiring harnesses with more than 50 connectors, 500 terminals, and about 1,600 feet or nearly 1/3 of a mile of wire. Mind-boggling? Yes. But a complete system is made up of separate circuits. So if you understand how basic circuits work, troubleshooting becomes a logical, orderly process. Let's begin our story with a review of basic principles. First of all, to make any circuit operate, we must have electrical pressure. In other words, electromotive force must be applied to produce electrical action in the circuit. When electrical pressure or voltage is applied to a circuit, it causes a flow or current which does the work. Headlights, ignition, blowers, and other equipment operate when electric current flows through them. As current flows through a circuit, it meets resistance in the wires and in the equipment. The electrical pressure must overcome this resistance, so the amount of pressure applied and total circuit resistance determine the rate of current flow. So in circuit operation, we are concerned with three interrelated electrical characteristics: pressure or electromotive force measured in volts, current or rate of electrical flow measured in amperes, and resistance measured in ohms. Since the voltage and resistance determine the current, we can expect certain results when either of them change. For example, increasing the voltage when the resistance stays the same increases the amperage or current flow. Decreasing the voltage reduces the flow. On the other hand, if the voltage does not change but the resistance increases, the current flow is less. Reducing the resistance allows more current to flow. This relationship is the basis of Ohm's law, which is used in calculating circuit values. Stated simply, Ohm's law boils down to this: a pressure of 1 volt will push a current of 1 ampere through a resistance of 1 ohm. Now, let's talk about circuits. An electrical circuit is simply a continuous path or conductor which allows electrical current to move from the pressure source around the path and return. However, in actual use, circuits can be arranged in different ways. To explain how this works, we can use a battery as a source of electrical pressure, light bulbs as a resistance load, and connecting wires. Consider the battery as an electrical pump operated by chemical action. It has a high-pressure side which causes electrical current to move through the circuit and a low-pressure side for its return. The connecting wires provide a continuous path from the high-pressure side of the battery to the low-pressure side, so current can flow in the circuit. To do useful work, the current must pass through the light bulbs connected in the circuit. The internal resistance of the bulbs provides the electrical load in the circuit. We call this a series circuit because there is only one path for current flow, and all the current must flow through each part of the circuit in succession. Any break along the line will stop the flow. The amperage is the same everywhere in the circuit, regardless of how many load units there are. The rate of current flow is determined by the total resistance in the circuit. However, the voltage or electrical pressure is used up as it pushes current through each successive resistance load in the circuit. Because of this, the voltage indication drops lower at the return side of each load unit. For example, if we begin with 12 volts and each bulb in our circuit drops the voltage by 6, you'll find 0 volts at the return wire to the battery. Adding all the voltage drops in the circuit equals the battery voltage. Now, in a parallel circuit, the light bulbs are connected so the current has more than one path. Part of the current flows through one and part through the other, so if one bulb burns out, the other will continue to operate. Unlike the series circuit, current flow in a parallel circuit may not be the same in all of its parts. The flow through each branch depends on the resistance in that branch only. Total current flow in a parallel circuit equals the sum of the flow in each of the branches. The reason? More current can flow through two paths than through one. The voltage at all branches of a parallel circuit is the same. Full battery voltage is available to all circuit loads. On a vehicle, we use a combination of these basic circuits with one main difference. Instead of running separate return wires, the body and frame structure is used as a common return conductor to the battery. Because of general usage, we call this the vehicle ground circuit. Now, let's see how our circuit know-how applies in troubleshooting electrical system problems. To begin, we'll talk about open circuits, wire-to-wire short circuits, and wire-to-ground short circuits. An open circuit is just that, a circuit which is not continuous and therefore does not conduct electrical current. A good example is a break in the main feed from the starter relay to the ammeter and fuse block. If this series circuit is opened at any point, all the circuits supplied by the fuse block are cut off. In like manner, a break in the feed conductor of a parallel circuit stops the current flow in its branches. However, a break in a branch conductor or the component it serves only affects that part of the circuit. Now, in a short circuit condition, we have a continuous conducting path, but depending on the kind of short, the current either flows into other circuits or it bypasses the circuit load and returns directly to the battery. In a wire-to-wire short circuit, the conductors of separate circuits contact each other at some point other than a common terminal. At the point of contact, current flowing in one circuit passes into the other. This means that current will flow in both circuits when either one is switched on. However, in a typical wire-to-ground short circuit, the feed wire contacts the ground return before it reaches the circuit load. Here, because the load resistance is bypassed, current flow can rise higher than normal and overload the circuit, blowing the fuse or cycling the circuit breaker. Another condition you may encounter is high circuit resistance, usually the result of loose or corroded connections or trouble in the component itself. Here we have higher than normal voltage drop, and as a result, abnormal component operation. A common example of high resistance is headlight output variation caused by a corroded connection at the front-end lighting circuit ground return terminal. The headlights are relatively dim at idle, but flare up noticeably when alternator output increases with engine speed. Another condition is circuit feedback, where current in one circuit finds a secondary path and operates components in another circuit, even though their normal power source is switched off. For example, the turn signal and hazard flasher circuits both operate the same light bulbs, but their power sources are at different points. Power for the turn signal circuit comes through the ignition switch, so the signals normally operate only when the ignition is switched on. However, the hazard signal circuit feeds from the battery through the fuse block and can operate when the ignition switch is on or off. If the hazard signals are operating with the ignition switched off and the turn signal lever is accidentally moved in either direction, it sets up a feedback condition. Current can now feed back from the signal lights through the turn signal switch and turn signal flasher, and from there to the accessory feed terminal on the ignition switch. If any connected accessory is turned on under these conditions, it will operate intermittently as power feeds back through the turn signal flasher. Before talking about troubleshooting, we better see how our simple circuits add up in actual use. To set the stage, here are some of the main wiring harnesses in a typical passenger car. For general orientation, we can separate these into the front-end lighting harness, the alternator harness, the instrument panel and steering column harness, and the body wiring harness. Obviously, there are other harnesses used on actual cars, but these will serve our purpose here. Note that the main harness connectors are located in the bulkhead, instrument panel, steering column, and left kick pad areas. These connectors provide access to the harness conductor terminals for testing. When checking, you'll need wiring diagrams to identify and trace the circuit conductors. All the main and accessory circuits for each model are diagrammed in your chassis and body service manuals. Now to our problem. The turn and hazard signals flash on both sides, but the stoplights do not operate. The first move, analyze the situation and apply our circuit know-how. From the wiring diagrams and actual observation, we know that the turn signal, hazard flasher, and stoplight circuits all feed the same filaments in the tail, stop, and turn signal light bulbs. So, if the turn and hazard signals flash, we know that the bulbs, bulb sockets, and socket ground contacts are in good working condition. Also, from the diagram, we know that the hazard flasher and stoplight circuits both feed from the same fuse. Because the lights operate, we know that the fuse is intact, but there is an open circuit somewhere between the fuse and the stoplight bulbs. We can trace the stoplight wires through the body and steering column connectors. However, since the turn and hazard circuits both operate properly, it is more logical to begin checking at the fuse end rather than at the body end of the stoplight circuit. At the stoplight switch terminals, our test light shows that there is voltage at the hot wire from the fuse. However, when the brake pedal is pushed, there is no indication at the other wire. No voltage at this wire tells us that the open circuit is in the stoplight switch. We can verify this by connecting a jumper across the switch terminals to close the circuit. Next, we're ready to check out short circuits. As mentioned earlier, a wire-to-wire short causes two circuits to operate when either one is switched on. Additional circuits may be involved where more than one circuit feeds from a single fuse. In this case, the simplest approach is to isolate the short circuit in a specific area by separating the wiring harness connectors, working from the component end toward the power supply. Switch on one of the circuits involved and check the wire terminals for voltage as you work toward the power supply. Note the connector where one of the circuits loses the voltage. The short is in the disconnected section of the harness. A wire-to-ground short circuit can also be isolated by separating the harness terminals and connectors. However, since a ground short overload blows the fuse, you'll have to connect a circuit breaker in its place when locating the trouble. Switch on the shorted circuit and work forward from the component connector until the circuit breaker stops clicking. The short is in the last section disconnected, including the component itself. In some cases, you can use an induction-type meter to track down a grounded short. Switch on the circuit and move the meter along the path of the harness. The pointer stops deflecting beyond the point of the short. High resistance in a circuit can be localized by checking the voltage drop at the circuit connections, beginning at the power source and working toward the grounded end. Clip the positive lead of a low-reading voltmeter to the power source. Then switch on the circuit and touch the negative meter lead clip to each succeeding connection in the circuit on the way to the grounded end. Continue checking until you reach a point where the voltage indication is distinctly higher than previous readings. The high resistance is between that terminal and the last point tested. And that rounds out our review of electrical system basics and general troubleshooting. We've been able to hit only the high spots here, but there's more to come in the session that follows, so don't miss it. When you put it all together using the wiring diagrams and other information in your chassis and body service manuals, even the tough ones should come easier.